In Lesson 5.9, inverse trigonometric functions, integration, we'll essentially do the exact reverse of what we did back in Lesson 5.8. That is, we're going to take a look at a class of functions that, upon integration, result in the inverse trig functions that we learned about in the last chapter. Specifically, we're going to be looking at the arcsine, the arctangent, and the arcsecant. All the arc co-functions are really just the negative versions of what we're going to explore in this chapter. So, you see, this particular lesson here is not entirely difficult, so long as you understood lesson 5.8. Now, towards the end of this lesson, we will look at some advanced examples where we're going to have to take an integral and split it up in a very special way in order to make things work for us. But we'll get there after a few rather easier examples, let's say. Anyway, all that being said, let's begin by simply defining the integrals of some of these special functions. This will be the box on the right side of your notes, and let's go ahead and fill it in now. So, as you look at this box to my right, you'll see the three types of functions that we're going to be dealing with in this lesson. Now, to be perfectly honest, all three of these should look familiar if you did your lesson 5.8 assignment anyway, or if you got those formulas in your head. You might notice that this first one looks very, very similar to the derivative of the arcsine. There's a little difference. Instead of 1 minus u squared under the radical in the denominator, this actually says a squared minus u squared. But it's only a slight difference. If we do have a function of this type, that will actually integrate into the arcsine of u over a. Now, of course, if a is 1, then it's just the arcsine of u plus c, and then we have the formula that we learned in the last lesson. But in a general case, if a is some constant other than 1, then it will result in arcsine u over a plus c. Now, how about this middle one, the du over a squared plus u squared? Of course, in lesson 5.8, it was du 1 plus u squared. But again, here we're going to introduce a constant. And so what that's going to do is actually give us 1 over a multiplied by the arctangent of u over a plus c. So this is a little bit different. Notice that there is a coefficient on this arctangent, and that is very important, unless, of course, a happens to be 1, and then we can just disregard that whole thing. Now, on this last part, this also looks very much like one of the derivatives from lesson 5.8. It is missing the absolute value on the u down here, but other than that, and the fact that we have an a squared instead of a 1 again, this actually is going to lead us to our arcsecant. It, again, will have a coefficient of 1 over a, and then what we'll do is we'll have our arcsecant, and here is where the absolute value is going to come into play. It'll be the absolute value of u divided by a, and then plus c. So again, I'm presenting these to you without proof, although you should be able to differentiate all three of these results and see where the integral comes from using the knowledge that you gained from lesson 5.8. And now that we've defined these integrals, let's go ahead and take a look at a few examples. We'll start with a few easy ones, and then we'll move into a few hard ones. But all in all, it will be fun and exciting. So let's go ahead and begin with A. So here in example A, you should be able to take a look at this integral and match it up to one of those three types of functions that we just explored in that box there. Of course, if I wanted to, I could rewrite this problem. How would I rewrite it? Well, I could take the dx and put it on top, and down below in the denominator, I could actually write 2 squared plus the quantity x minus 1 squared. Why would I go about doing that? Well, quite simply, I can now see what my values for a and u would be. And in fact, if a is 2, which seems to be the case here, and u is quantity x minus 1, which also seems to be the case, then I can conclude that du must equal 1 dx. And so there is my du right there on top. Wow, this perfectly matches the integral formula that results in the arctan. And in fact, that's what I'm going to do here. Now that I know what a and u are, and I see that my du is present, I can simply write that this entire thing is simply going to be equal to 1 over a multiplied by the arctangent of u over a plus c. And that is my final result. The original integral matched the formula perfectly and gave me my arctan. Now, if you want to prove this to yourself, which I'm sure you do, of course, go ahead and use the derivative formulas that we learned in lesson 5.8 and apply those to our answer here and see if your result isn't exactly where we started. Give it a shot and you'll see that it does work out. Alright, so we're going to go ahead and take a look at example B, which looks awful. There's an arc cosine in the problem. How in the world are we going to handle that? Well, think about it first, pause the video, give it a quick shot, and then I will join you at example B. Oh boy, so what are we going to do here in example B, where we have an arc cosine inside the integral? What a giant mess! Unless we realize that if we were to call the arc cosine of x u, watch the beauty that would happen. If that is u, do you recall what du would be then? If you forgot, just go ahead and take a look back at your 5.8 notes. But if u is arc cosine of x, then du is simply going to be negative 1 over the square root of 1 minus x squared dx. And quite fortunately, that's almost exactly what I have in this problem. In fact, if I were to rewrite this, the only big difference is that I would need this negative that I have right here. And so I'm going to go ahead and just toss my negative in there and balance it out with a negative on the outside. And what this problem is actually going to become is negative the integral. I'll keep my bounds in terms of x with the expectation that after a u substitution I'll unsubstitute back. Let's see here. The arc cosine of x, well, that's just u. And the negative, all this stuff and all this, that's simply going to be du. So there's my integral under the u substitution. If I go ahead and integrate this, what I'm going to end up with is negative 1/2 u squared. And, well, I better unsubstitute that before I show the bounds. So this is actually going to be negative 1/2 arc cosine squared. Let's see, arc cosine x squared, I should say. And those bounds are going to be, again, from 0 to 1 over square root of 2. Now, am I able to handle these? Well, let me go ahead and just bring down my negative 1/2. No issues there. If I plug 1 over the square root of 2 into my arc cosine x, and then square it, well, if I plug it in, I'm going to get pi over 4. If you know your unit circle, you know that. The arc cosine of 1 over radical 2. Maybe you don't like 1 over radical 2. Remember, that's the same as square root of 2 over 2, if that helps at all. So the arc cosine of that is pi over 4, and if we square that, we'll simply get pi squared over 4 squared. And then, if I plug 0 into the arc cosine of x, well, let's think about that. The cosine of what would give me 0? And of course, that's just pi over 2. So if I square that, I'll simply get pi squared over 2 squared. So I feel like I'm almost there. There's my negative 1/2. If I find a common denominator and do a little bit of work to this, what I'm going to get is, let's see here, negative 3 pi squared over 16. You should be able to do the arithmetic for that. And then our final result, if I just multiply these two things together, I'm going to get 3 pi squared over 32. If you like, you can use the integration capabilities of your graphing calculator to see that it does come out to some decimal, which if you then go ahead and type this answer in, will be the exact same decimal. So you see that it is actually correct. Although, of course, what we have here is much better than a decimal in that it is exact. So good times. All right. So even when we have arc cosine or arc tan or arc sine or arc anything, if we have that inside the integral, consider a u du substitution where u equals that inverse trig function, and hopefully du will show up somewhere in the problem. Hopefully. Alright, well with that, let's take a look at one more example before we get to the tough ones. This next one, example D, which seems to be written interestingly on this paper, but either way, example D really is not too bad. you should be able to do this without my assistance. So go ahead and give it a shot, and when you're ready, please join me again. Here in example D, we're going to need to integrate this function here and see what we end up with. And this is a definite integral, so we can absolutely evaluate it and see what this whole thing equals. Now, again, feel free to run this through your graphing calculator and see what decimal it gives you. But let's try it out ourselves and see if we can get the exact answer. Now, taking a look at this should absolutely ring a bell for you. It looks very much like one of those formulas in the box that we need to know, and in fact it is. If we were to call a the square root of 3, and u can be x minus 2, which of course then means du is simply going to be dx, then what we have here is an arctan. We have 1 over a squared plus u squared. That's an arctan. So, without doing any substitutions or anything like that, I'm just going to go ahead and write the result of this integral, which would be 1 over the square root of 3 multiplied by the arctangent of x minus 2 over square root of 3. Now, I don't need to put the plus c because this does have bounds on it of 1 and 2. So what happens when I plug those bounds in? Well, here's my 1 over square root of 3. First, I need to think, what is the arctangent of 0? When I plug 2 in here, I get 0. And the arctangent of 0, of course, is just 0. When I plug the 1 in here, I'm going to get the arctangent of negative 1 over square root of 3. And if you need to remember, negative 1 over square root of 3 is the same as saying negative square root of 3 over 3. So I don't know if that helps ring any bells for you as far as the unit circle goes. But either way, this is going to be negative pi over 6. And so it looks like what this is going to result in is simply going to be pi over 6 square roots of 3. Now, if you want to go ahead and rationalize that, be my guest if you don't like having radicals in the bottom or whatever the case. As for me, I'm going to leave it the way it is. It's perfectly acceptable. And if you run it through a calculator, see what decimal it gives you, and see if it isn't the same decimal that you got when you typed the original numerical integral into your calculator. It should be the same, unless, of course, you're typing in your calculator wrong, but that's a whole nother issue. So, with all that, let's go ahead and take a look at example C, the fourth example in these notes, where things are going to start getting a little bit hairy. Certainly, you should try this problem out before we get there. I don't expect you to be able to do it without assistance, although it would be pretty sweet if you could. Give it a shot, and then we'll do example C together. In all truth and honesty, I consider this example C to be the hardest problem of these notes. And if you've already tried the problem, you know why I posit this. But if you haven't tried the problem yet, go ahead and take a look at it. Certainly, the denominator makes it look as if I'm dealing with an arctangent. I can see that my a is going to be 2, and my u will be x plus 1. But when you look in the numerator, I have x minus 2. That is an issue, because du is just going to be dx, and my dx is hanging out right there. And I can deal with a constant, because I can always take a constant and move it outside the integral, but this x is really going to mess me up. How do we deal with this? Well, we need to actually consider that this integral might need to be split into two integrals. And how are we going to do that? Well, this is going to be tricky, but if we consider the entire denominator to be u, so u is actually quantity x plus 1 squared plus 4, then our du, as you can see, would simply be 2 quantity x plus 1 dx. And that I can kind of make happen on the top. You see, I don't actually have a 2x on top, but I could multiply this by 2 and end up with a 2x that way. In fact, let's see how this would look. If I do want to multiply by 2 on the top, so I want to have 2 and then quantity x plus 1, well, of course, to do that, I would need to multiply by 1/2 on the outside. That will bring harmony back to this integral, and I'll keep the bottom as it is. So there we go. to quantity x plus 1. Now, remember, this is not actually x plus 1. This is actually saying 2x plus 2. And so, if this is plus 2, I'm going to have some interesting things going on here. And I take that back, actually. Let me retract that statement. This is x plus 1, but because of the 1/2 and the 2, those are going to cancel, and now I'm just confusing matters. So let me be quiet there. If this is x plus 1, what more do I need to restore the integral back to the way I started with the x minus 2? You might realize that, well, essentially, all I need to do is subtract a 3. Does that make sense? Well, if I have the 1 and I subtract 3, what would that give me? 1 minus 3, there's my negative 2. So if I do this, as ugly as it looks and as confusing as it might be, this split of integrals is actually equal to my original problem. Alright, so you see how this works. I treated the entire denominator as u, and I forced du to happen in the numerator. And then whatever was left over, that just became another integral. And now that I've done that, this actually is not going to be too bad. And right here, because the top is a derivative of the bottom, remember, this is essentially du on top, and it is essentially u on the bottom. Well, what that's going to give me is 1/2 times the natural logarithm of quantity x plus 1 squared plus 4. Now, you might be mad that I'm not putting that in absolute values, but think about this. This quantity x plus 1 squared plus 4 can never be negative anyway, so the absolute values are kind of unnecessary. It's not wrong if you put them, but there's really no reason to. Now, as for this second part, this is just a very standard arctan. I see that a is going to be 2, u is going to be quantity x plus 1, and that of course means du is just going to be dx. So if I want to, I can take my 3 and move it out front of the integral. It really doesn't matter, because what I'm going to end up with here is simply 3/2 multiplied by the arctangent of quantity x plus 1 over 2, and then I will add my constant on. So although it might look kind of ugly, this is the actual integration of our original problem. Why does it look so ugly? Well, at first, it didn't really fit any of our arc function formulas, and so I had to play around with it a little bit. You see that I did a u du using the denominator as u and forcing du into the numerator. And then whatever was left over, in this case the 3, whatever was left over became my second integral, and then I just did 2 problems for the price of 1. And that's always a good time as well. So, we have one more example that's kind of like this, so we can take another look at it. This next one is going to be example E. As the directions state, before we get to example E, you might want to notice that we might need to complete the square, and I am going to tell you that in example E, we will need to complete the square. So if you want to go ahead and give it a shot, pause the video, try it out, and then join me on example E. Although I posit that example E has a lot of similarities to the example C that we just did, we are going to have to complete the square if necessary. And on this particular problem, well, it's necessary. So if we want to complete the square, I'm not going to go through all the mechanics of how to complete the square. If you need to know that, of course, I certainly encourage you to go back and speak to your Algebra 2 teacher. But for the sake of this, I will say that the square will be x squared plus 2x plus 1. And then, of course, left over from there, to get to the plus 2, we just have another plus 1 kind of hanging out. And what that means is that our actual integral that we're going to be dealing with here is going to say 2x minus 5 on top, and on the bottom we'll have quantity x plus 1 squared plus 1, and don't forget the dx. So here is the completed square version of our original problem, and this is what we're going to be dealing with. Now, at this stage, we have to go back to the last example we did and see that it's in fact very, very, very similar. In this situation, if I let u be the denominator, that will be quantity x plus 1 squared plus 1, which means that du is going to be 2x plus 2. And of course, there's my dx. So I can do a little separating of this integral, and let's see what that would look like if I want to do this. I'll leave the bottom the way it is, the quantity x plus 1 squared plus 1. That will be my u. Du, what I want on top, is simply going to be 2x plus 2. Fortunately, this time around, I don't need to deal with the 1/2 and the 2 and all that good stuff, because the 2x is already given to me in the problem. So, there we go. What kind of integral do I need to add in order to restore myself back to the original problem? Of course, my denominator will still be the same, no change there. But my original problem was 2x minus 5. Here I've pulled out 2x plus 2. What do I need to add to 2x plus 2 to turn it back into 2x minus 5? And that, of course, is just negative 7. So at this stage, I can go ahead and complete this entire thing. This first part right here, the top is a derivative of the bottom. So this is simply going to give me the natural log of, let's see, this will be, I can do absolute value if I want to, I guess. Quantity x plus 1 squared plus 1. And that will be the first part of the integral right here. And then the next part, this integral, will actually say minus 7 times the arctangent of quantity x plus 1 over 1, and then plus c. So there is my final answer. Again, this could be an absolute values. It doesn't necessarily need to be, because this value is always going to be positive anyhow. There's no value of x that will make this negative. But either way suffices. The important thing here is this step right here, where we figure out how to separate the integral into two parts. One that can be done with a u/du substitution, and one that represents an inverse trig integration. And as long as you're okay with that, you will be fine. Fortunately, you'll get a couple chances to practice this skill in the assignment. But before we get there, let's do one more example. Example F is deceptively easy. Give it a shot before I do it, and I'll meet you there. In example F, we learn that complete the square if necessary does not always mean complete the square. It's not always necessary. In fact, in this particular problem, you might be tempted to go ahead and complete the square and try to force this to look like an arcsine kind of function. That I could see why you would do that. There is a square root on the bottom, and that does look like an arcsine. But if we simply call u x squared minus 2x, then look what du would be. That would simply be 2x minus 2 dx. And maybe you can see where I'm going with this. This does not even need the arc functions. In fact, if I go ahead and multiply the entire numerator by 2 and balance that with a 1/2 on the outside, then this problem actually becomes 1/2 of u to the negative 1/2 du. There's no arc function. It's not always necessary to make it look like arcsine or arctan or arcsecant. If it's easy, let it be easy. Always try the simple u substitutions first. Anyway, moving on with this, we of course know how to integrate that. If we do that, we will simply get 2u to the positive 1/2 plus c, of course. The 2 and the 1/2 cancel, and notice that all I'm left with here is quite simply u to the 1/2 power. So there's the 1/2 power. There is my u. There's my constant of integration. And that's as easy as this problem is. Don't be tempted to always use the arc functions just because we're in the arc function lesson. Still, use your mind. Alright, so now that we have completed these lesson 5.9 notes dealing with inverse trig functions and integrations that lead to those, you've seen hopefully that this lesson, lesson 5.9, is actually just simply the reverse of lesson 5.8. In lesson 5.8, we differentiated arc functions. In lesson 5.9, we integrated, resulting in arc functions. So that's pretty cool. The good thing about all this stuff is there's actually only three formulas that you need to know: the arcsine, the arctangent, and the arcsecant. Now, granted, these notes were very, very arctangent heavy. In fact, how many of these examples dealt with arctangent? Quite a few of them. But don't be fooled. Arcsine, arctangent, arcsecant, they occur in pretty even doses. Not everything is always arctangent, although it kind of seemed like that in these notes. So you only need to know those three formulas, because if you have the negative of them, then you can simply balance it with a negative inside and a negative outside, resulting back into an arc function again. The hardest part of these notes, perhaps, were examples where we had to take the integral and split it into two parts, one representing the u du substitution, and one representing the integral that led to an arc function. Those were a little confusing, but with enough practice, they're not so bad. My advice: let the denominator equal u, and then force the numerator to be du. Whatever's left over from that, make that a new integral, and that will probably be your arc function. So, we didn't cover, again, a whole lot in this lesson, but what we did cover was quite interesting in that it was just the flip of the previous lesson. Pretty cool. So remember all these things, and good luck with your assignment.